I guess I can just reflect 3 random points. But I'm going to have to rename some things, obviously. We call these A, B, and C. A, B, B, E, and CF. Let's call this P, Q, and R. P, oops, Q, and this is R. The points X, Y, and Z lie on EF, FD, and DE, so that AX is parallel to BY, is parallel to CZ, is parallel to L. Interesting. So let's move E a little farther back. Okay, so we're going to draw the parallels A, B, and C. And so let's make these rays. EF and FD. Okay, so PQR is really line L. And let me think how to do this. Let's make a nice diagram. So X lies on EF. So we have these parallels and we want them to meet those lines at nice points. I'd rather PR be horizontal, and then okay, so basically we draw these 3 parallel lines and we want to see where they meet these 3. So yeah, something like this. So Y lies on FD. Oh, FD is annoying. Okay. Okay, what I think we really want is something like this, so that all the, okay, so X lies on EF, so this is X, and Y lies on FD. I'll draw Z first. Z, this would be Z. And sorry, that should have been Z. I don't know. It should be C. I want to make FD, yeah, something like this. And we want to show X, Y, and Z are collinear. This should be Y. Okay, I think that's good. So, yeah, I'm just trying to make it a nice diagram. Okay.
We can try Menelaus on DEF.
Okay. Let's see. I'm going to draw a couple points. I'll draw this and this. And hide the rest. So, I don't really need that point. I'll just draw this. Maybe I'll draw this point too, right here. I think that's good for now. Yeah, I'd like to make DF flatter, but it would make the diagram harder to see. So yeah, you want to try Menelaus on DEF. Let's see. So that would be something about DE over DZ, EF over FX, and FD over FY, I think, right? What's the relationship that has to hold between those so that X, Y, and Z are collinear? Sorry, doing this. Let's see. All right. So what's the relationship between DE and EZ, EF and EX, and DF and DY that makes X, Y, and Z collinear? Is there some nice formula or something? Let's see. So like if x, y, and z were collinear, we'd have like yx over yz times zb over de times ef over fx equals 1. But if we don't know that they're collinear, then how do we use those lengths to figure that out? So yeah, is there a general theorem that says not sure. Like if you have a triangle and then you have 3 points on these 3 rays, like let's say you know KL, LM, and KM. Is there any condition on these other segments that tells you if N, S, and O are collinear? Um, I feel like that would be really helpful if there was a formula like that. I just don't know what it is. Let me see if I can look it up. So is it like, there's got to be some formula. Is it like ED over EX times, looks like Khan had hop off, or maybe he got disconnected. But Is it like ED over EX times EF over XF? I don't know exactly what the formula is that would make those collinear. But yeah. Let's see. I think everything with Menelaus can be proved instead using like cross ratios. So if we want to show x, y, and z are collinear, can we project through anything? So if they were collinear, I'd want to project, see if I can project x, y, z, but we don't have a point at infinity. That's the thing. I don't think those are actually collinear. I'd be very surprised. Let's see. Yeah, no, that's not actually collinear. Let me see if I can just first relate these, and then we could try using Menelaus after that. So DE and DZ. What do we know about that? Yeah, that's such a weird problem. I don't know if it could like form parallelograms or something. Let's draw this whole line. Draw this line. We don't know this line. We don't know they're collinear yet, but if they were, then we'd have like this point right here. And it's a very unusual kind of problem. Let's see. We could spend another like 15 minutes on it, or I don't know, maybe 10 minutes, then move on. So we can try to calculate the distance from z, x, y, and z to this line. And then I wonder if we can drop perpendiculars to the line. If we could show that like ZL over LK is XM over MK is YN over NK. Depends how we define K though, because we don't know that these are linear. So actually we could get rid of point K. Oh, is that some lemma that helps with this? Let's see. Is there a certain lemma that you wanted me to look at? Sorry. Page 6 footnote. Okay. Open the place. This. If ABC are 3 collinear points and P is not on the line ABC, I've never seen this before. Okay. So we have 3 collinear points and a point not on the line, and points on line PA, PB, and PC. Okay, so we have to show okay, so it's like we know DE, EF, and DF. So those would be these 3 values. And then it would be point P would be actually, now I wonder. Let me read that one more time. So what would P be in this case? Oh, maybe P is the point at infinity on line PQR in this case. Not sure. Yeah, I'm not sure if that theorem applies here. It's interesting, but we don't have like 3 collinear points and then a point P that's off those 3 collinear points. So yeah, I don't know if it applies. See what I'm saying? Yeah, I'm not sure how to apply that here. Okay, so if we draw perpendiculars, we want to show that xm is like a weighted average of zl and yn. So we want to show, I think we want to show xm is zl times mn over ln plus yn times ml over ln. So CZ is parallel to L. So let's see. ZL is the distance from F to PQR, right? And XM is the distance from E to PQR. And YN, let me see, did I get that right? YN is the distance from E to PQR. So these 3 segments, their lengths are the distances from D, E, and F to PQR, to that line. So, and we need to show that one is like a weighted average of the other 2. So we need to know like MN and ML. And I think maybe this isn't as hard as it looks. So the distance MN that's not that easy to compute, I guess. Yeah, if we can find MN and ML in terms of like D, E, and F, then I think that would help a lot. So MN, see what time it is. I don't want to do this from forever, but I think if we make some progress, we can keep going. MN Yeah, so the distance, this is really tricky. How do we figure out MN? So what we could do is we could draw, so X, Y, we could try this. If I draw the perpendicular here, MN, it's the distance from X to this line minus the distance from Y to this line. I don't like that picture. So X is on EF and Y is on FD. If I draw this perpendicular, MN is YS minus XO and YS. So Y lies on FD. YS. So YS we can calculate in terms of, yeah, like FS and FO. Yeah, I feel like this might be bashable, but it might be an ugly, ugly bash. Yeah, like for example, if we drop all the perpendiculars from D and F to the line, then YS over FS is YT over TD. What we need is we need the difference YS minus XO. That's a tricky thing to calculate. All right, let's move on to another problem. See if we can figure out something else. This was the one we ended on last time, which I really like. Let's try an easier one first. So let's try this one. Maybe this one isn't as hard as it looks. So these converge at a point M, or concur at M. and this is A naught. Okay. So then we draw the circles with diameters BC, AC, and AB. So yeah, let's try to not make these, let's try to make these far away from the midpoints as possible. We have 1, 2, 3. I'm going to draw those circles. I could have just drawn the altitudes, but the feet of the altitudes, this works. Okay. And we want to see where it intersects A naught, B naught, and C naught. So let's draw it like that almost. And then so we have those three, and then we have the three altitudes, obviously, that concur at the orthocenter. But so this should be H. I'm going to rename the other H, well, J, and kind of like this picture. I'm going to hide, I feel like these points are distracting, so I'm just going to hide them for now. So we want to see, where does A naught meet the circle? So we should make it like a ray, and then B naught and C naught. I'm wondering if this might be not that hard, but I'm not sure. So this B naught meets those two circles, and C naught. Oh, the circle with diameter A naught. That makes it tricky. All right. So then I need the midpoints of A naught, B naught, C naught. But the circle with diameter A naught is A naught. So that helps, right? So yeah, basically we got these 2 points. A1 and A2. Okay. What is H? No, I just want this to be J, not HJ. So that's one circle, and then here's the other circle. A C naught. Actually, let me think about this. Sorry, C naught and I. B naught and B naught and J. So
PowerPoint finishes this, I think.
yeah, I'm sorry, I'm getting a little confused here, but I think we can label these 2 points right here. So this would be B1.
Yeah, this is true. Okay.
So first, is it true that those are cyclic? First, let's try to show that just those 4 are cyclic. And it's not enough to show that these 4 are cyclic and these 4 are cyclic and these 4 are cyclic.
Notice
They
that
can all lie on 3 different circles. So you have to show that all 6 lie on the same circle. And maybe there's something special about this circle. So I wonder if B2H and B1, it looks like they're collinear. So that might be a big step towards showing this. It might just be power of a point, actually.
Yes.
When we show H lies on the radical axis, like maybe we could start by showing H lies on the radical axis of all these circles. So this one, it's the circle. The power of H with respect to this circle is BH times HJ. And it's the same as the power of H with respect to this circle. So that means that, let me think about this. And is it also the same as the power of H with respect to this circle? Yes. So that
H has
that
respect to this big circle.
Basically, all the points are collinear. BH, B1H and B2, A1H and A2, and the powers. Yeah, I think this is trivial, isn't it? I think it's much easier than it looks.
Yes.
Let me think about this. So I'll say like label the points as shown. It just looks hard, but it's actually really easy. So first of all, we want to show H lies on the radical axis of these 2 circles. So for this one, BH times HJ is the power of it with respect to that one. And AH times HG is the power with respect to that one, but those are equal. So yeah, I'll write it like this: power of H with respect to the circle AGA naught is equal to AH times HG, which is equal to BH times HJ, which is equal to the power of H with respect to the circle BJ B naught. Okay. And therefore, let's see if this fixes it. Just leave it like that. Yeah. So HA1 times H, yeah, that's like how you finish it, right? So this shows that this shows that H, B1, and B2 are collinear, right? Let me see. So this circle is BJ B naught, and this circle Oh, maybe I didn't do this right. Let's see. So A naught. Did I do the wrong circle? Maybe. So oh, this shows that A1, H, and A2 are collinear, I think, because it's the intersection of this circle and this circle. Okay, so this circle I should change it to be BJC. Is that right? So yeah, circle B. I'll just write it like this: the circle with diameter BC. Okay, so that means that H, A1, and A2 are collinear. And then similar for E1, E2, and C1, C2, and then I'll just copy what you wrote. So yeah, this is an easy problem. I think, yeah, HA times HG. Just going to make it look nice, but then, yeah, then we can move on to that other problem. All right. So that means A1, that means it's cyclic, yeah. All right. Let's try that problem from the last session that we worked on. So let's try this one. So we have three similar rectangles that are built off of triangle ABC. And we draw B prime and C prime like this. So we let DL intersect KZ and EF, B prime and C prime. And we want to show that AA prime bisects B prime C prime. So I drew in these extra lines. I drew in point J. It wasn't there originally. I just thought it might be helpful, but I don't know for sure. Let's see. Can we use projective geometry? So we want to show that B prime, G prime, C prime infinity is harmonic. And if we project those through A prime onto FZ, then that's the same as showing that FJZIF is harmonic. That's why I did that originally. We have the parallel through A prime to DL. Now, is there something else we can project it through? That's an interesting question. I think they should. Yeah, they should concur at the orthocenter thing. Oh no, those aren't the circles with diameters AB, but no, they don't. Let's see. There are, it is interesting though. There's like this point.
Yes, yes. Mm.
So every two of them concur. Like if you drop a perpendicular from B to EF, these two will concur on that. But yeah, it's not like all three of them concur. I'm gonna hide them for now, unless we can, well.
Obviously, because 90-degree C intersection. Sorry, sir.
That's kind of interesting. BB, is that really true that BB prime? Yeah, no, it doesn't meet on that circle. What if, I guess another thing I could do, I could draw this point and this point, and then we want to show KEH and M are harmonic. And then I could try projecting those through A instead. I kind of like that idea. So first I project through A prime, and I want to show that KEHM is harmonic. And then I could try projecting through A, but I'm not sure what I would project onto. That's the thing. I could try projecting onto the circumcircle of ABC. So this is a right angle, angle KAC. So is EAB. So like for example, if I project E through A, I get the antipode of B, and if I project K through A, I get the antipode of C. So let me get rid of point J, and let me just keep point H. I like point H better. I feel like it'll make the diagram easier to see. So, and I want it to make the triangle so like almost like a right triangle. Okay, so something like this. I'm projecting through A onto this circle. So this would go to the antipode of B, and K would go to the antipode of C, and M would go to just some other point that I don't know yet. Okay, so like this. So this is the antipode of B, antipode of C. I'll call it B1. And this I'll call like C1. And I'll call the center of the circle O. So we have a rectangle, BC1, B1O. And H, A prime H is parallel to DL. So that's how this figure works. Okay, let me hide stuff. So ultimately, so I projected those. And now I need to project AH onto the circle. And then I need to show that that's a harmonic quadrilateral. So PNB1C1, I want to show that that's harmonic. Oops. So B1C1, that's like parallel to BC. And I wonder, so we want to show these are harmonic. Maybe there's a way that basically means that these are collinear. Like if we can show H, so the problem's equivalent to showing H, Q, and this point, which we'll call R. If we can show H, Q, and R collinear, that also solves it.
Isn't it obvious? Because
So yeah, we have a couple different ways of thinking about it. So let's see, P and N. Okay, so PNB1C1. Yeah, there's nothing special about that. We could try projecting, let's see. So yeah, I like trying to show that those are collinear. I think that might be a good way to just try it. What can we say about this line right here? Maybe, let's see if these are cyclic. I don't think so, it doesn't look cyclic. But yeah, I guess another way to phrase the problem is we could let RQ, because R and Q are kind of easy to define. So we could let RQ meet KE at H, And then we could try to show that HA prime is parallel to DL. That's one way to do it. I kind of like this way because that lets us do a lot of projections. Because then we already know that KMEH is harmonic. And we're just trying to show that A prime H is parallel. See what time it is. We have about a half hour left. So Q is just where KZ meets AE, and R is where EF meets AK, and then QR we let it meet EK at H, and we want to show HA prime is parallel. I like that way of doing it. So if we want to show they're parallel, what's a good way? I would be very surprised if these actually concurred, but let's see. Yeah, it's not true. Is there any kind of similar triangles? Almost looks like HB prime, but yeah, there's no way it's parallel to BC. You know? Let's see. Just playing around here. I wonder if there's anything special about point H. Doesn't look like it. Like maybe we could let both DL and HK intersect KE. We could try to show similar triangles. So yeah, that would be equivalent to showing. Let's think about that. We could try to show HKA prime is similar to SKB prime. That would be one way to do it. So we can use Menelaus. So HE over HK times KQ over QA times AR over RE equals 1. Or A prime R over RE equals 1. I think how that could show these are parallel. See if there's anything about point S that's special. Are those collinear? ST, no. Yeah, I'm not sure what to do here. Yeah, I feel like this might be a lot harder than it looks, this problem. Let's see if I draw this. We could try to show like MH over MA prime is MS over MG. That would solve it. Then MS. Let's try it for like 5 more minutes. I like the approach of showing NP, B1, and C1. What if we stuck with that? Because the tangents at B1 and C1, like we know what that is pretty well, like where they intersect. And basically we're showing Pn passes through that point. If I move the diagram around, that's kind of messy, but let me just think about it. All right, let's try something else. We might end up finding an easy problem, but let's see. So we did those. Oh, this one we didn't finish. Let's try, did we do this? I don't think we did this one. Let's try it. So this problem, let's see where it's from. Not that. I am not sure where this is from. Oh, this is a Mathlinks contest. That's where it's from. Okay. Okay, so D is this point. I'll label the end center. Why not label D, E, and F? And the center of this will be I. M is the point such that AM is parallel to BC. Okay. And it's kind of well known that this point, I think the mixed linear touch point are collinear. I think that's true. I can check that. I think that is the case. Oh, that's what we're trying to prove in the problem. Yeah. So this is kind of a well-known theorem, but let's see if I can prove it again, because I haven't seen it in a while. Okay, so we want to draw the mixed linear in the circle. So we could do it like this. And draw these two, and then this should be the center of the mixed linear in the circle right here, and J. There we go. So it's showing MD and this point are collinear. I know I've seen this before. I think it's an EGMO, pretty sure. But let's try to prove it ourselves. Okay.
Yeah, this is trivial if we
Do
know.
you know the proof?
Yes.
I know I've seen it before. So we know a couple things. We know that KG passes through the midpoint of this arc, and we know that KH passes through the midpoint of this arc, and we know that KI passes through the midpoint of arc AM. So we know all those things. And I actually proved those in a previous video of mine. On mixed linear in circles. So yeah, point V keeps disappearing. We have this, and we have this, and this, and then we have these two. And we want to show that K, B, and M are linear. Can we use a homotopy somehow? So
Basically, it is equivalent to
so
so.
D is like the bottommost point of this circle. Let me draw it a little nicer so that, well, I think it's fine actually. So really we need to calculate angle KDB, and I think we might have some similar triangles. Yeah, I kind of like that picture better. So angle KDB, if we can calculate that, I think that would probably solve the problem.
ABK is similar to KDC.
So KBL, is that similar to some other triangle? Forgot a lot of these proofs. Or I think KBL and KDC might be similar. I think that might be the proof. So KBL, that's 138 degrees, and KDC, they're not. Did I draw that right? So wait, KDC, that's 117. Maybe it's KBG. KBG, that's what it is. Okay. ABK is similar to ABK is similar to KDC. Okay. And so from there, we can calculate angle K, so KDC. Then I think it's just an angle chase after that, right?
Yes.
So basically, so let's see how we prove those are similar. So one angle is obvious. And then we want to show CD over CK is AB over AK. But that's the same as CH over CK. And So yeah, and how do we show that they're similar? Is it oh yeah, once we show they're similar, it's trivial because then that means angle AKB is CKD, and so yeah, they would intercept equal arcs, and so it would be true. Okay. So can we show the ratios CD over CK is AB over AK? I guess that's the question. So CD over CK, that's CE over CK. And I wonder if CEK is similar to something. CEK, is it similar to CAK?
Yes, plus this.
Okay, so we're saying there's a spiral similarity. Okay, so it's equivalent to saying KDB is similar to KCA. We're saying there's, yeah, a spiral similarity.
CO2 plus this angle.
Yeah, is it obvious? Like, how do we know that ABK is similar to KDC? That is the question. Can we use the angle bisector theorem somewhere? Do we have any harmonic quadrilaterals? It's interesting. We know that L and O are the midpoints of those arcs. Yeah, what can we say about the segment CK? So is BKC similar to some other triangle? So I wonder, we're saying KDC and KBA are similar. So we're saying there's like a spiral similarity. How do we know that?
Okay, draw the touch point of AX circle.
Maybe. There has to be some other similar triangles that I'm missing. So I wonder what the whole triangle KBC goes to under that spiral similarity. So, like if it went to some other point, like like right here, then we would want this angle equal KBC. There's got to be a harmonic quad somewhere. Like I feel like whenever you see mixed linears, there's always like a harmonic quad. So there's got to be some other similar triangle. So KC, is KCI similar to something? KCI and maybe KCI is similar to KDB. Is that right? I don't know about
KCI.
that, but let me check it. So KDB is equals KCA.
Okay, I have found the way. Proof. Can you hear me? Hello?
Oh, that's not right. Sorry. Why did I make a point P? That
Hello?
is equal to this. And it's not that. Okay. Oh, I can't. Yeah, I can't hear you. Oh, I think you're on mute. I can unmute you.
Okay. So K prime be the point such that
Oh,
like
are you speaking now?
draw a line parallel to BC through K.
But yeah, I don't hear you. So maybe you could type it in the chat. Hmm. So yeah, type it up in the chat. I don't know why it's not working. Draw a line through K parallel to BA. All right. Oh, BC, sorry. Do I draw this point? K prime. Now AK and AK prime are orthogonal. Yes, I agree. All right. So CKD equals BK prime A. Why? Let me think about that. I don't understand that part. So why does CKD equal BK prime A? I understand that they're orthogonal. But how are you using that D as the point of tangent C? Because A, K prime, and the touch point of the AX circle are collinear. Is that a well-known fact? So A, K prime, and the touch point are collinear. Is that just like a well-known fact, or is that obvious? Maybe that's a well-known fact, so you're using that to prove this. Okay, it's part of the mixed linear configuration. I wonder if that's really easier to prove than showing that KM and B are collinear. But yeah, for now, I'll take it as a well-known fact. Okay. So, and yeah, once we know that, there's like a symmetry. Yeah, like once we know that, then there's like a symmetry that shows that K, D, and M are going to be collinear. Because if A, K prime, and P are collinear, then if you reflect them all over the perpendicular bisector of BC, then K, D, and M have to be collinear, right? Okay, so if we use that fact, then P, D, and M are collinear. Okay, let me see what time it is. All right, so it's 12 o'clock. So we are going to stop here. Whoops, this thing doesn't move. But yeah, so thanks a lot for participating on the session. We got through a good number of problems, and for everyone watching on YouTube, thanks for watching. So if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So thanks again, and have a great day.